Hello everyone, today we'll be discussing some important problems from the chapter coordination compounds. These problems would mainly cover concepts related to nomenclature, isomerism and magnetic properties of coordination compounds. So let's start with the first question. In the first question, you are asked to write the IUPAC name of a coordination compound which is given. A set of ligand groups are attached to the central metal atom. So let's proceed with the solution.
So to approach this question, we'll have to see what all ligand groups are attached to the central metal atom. In this case, we have a bromo group. We have H2O, which we write as aqua, right? We have an amine group, so we write that with a double M, amine. And because it is 4 of them are there, so we write tetraamine. Now in this case, you will have to see what is the first letter. We'll have to attach them alphabetically. So in this case, the first one is amine. Second is aqua because it's AQ, and the third one will be bromo. So we will write it in this order. Also, we know that the group attached outside the metal atom is nitrate, and we can find the valency on the carbonyl on the atom, on the central metal atom. So that is, let that be X, and we can say -1 for bromo, and the others are all 0 valency compounds. So we can write this is equal to +2 because a nitro group will give -1 each. So X is equal to +3. So we can say that +3 is the charge on the metal atom. So thus the compound's name will be tetraamine. Aqua, bromo, cobalt. We can write 3 in Roman numerals. Nitrate. So this will be the answer for the question.
Okay, so as you have seen, this question covers all the concepts related to the nomenclature of coordination compounds. Basically, you need to know the names of all the ligand groups which are most commonly used and commonly asked in examinations, and also you need to find out the valency, which we have told you how to do it, and thus you'll be able to tackle most of the problems related to nomenclature. So question number 2 states that the complex ion which has no d electrons on the central metal atom is. So out of the following 4 options, you need to find out the coordination compound which has no d electrons on the central metal atom. So let's see how we'll come up with the solution.
So to approach this question, we'll have to find for each option, we'll have to check what is the charge on the central metal atom. In the first case, we'll have to see it is 4O2 minus that we have. So we'll let Mn be x. X minus 8 is equal to -1. So we can say x is equal to +7. So we know that this is +7. For the second case, we'll have to check again the same way. X plus 0 is equal to +3.
Right.
So we know that x is +3 in this case. The charge on the metal atom is +3.
Okay.
For the third case, again we'll have to follow the same procedure. In this case, we know Cn is negatively charged, Cn minus. So we know it is x minus 6 is equal to -3. So x is equal to +3. And similarly for the D option, we'll have to calculate, let CR be x again. So x plus 0 is equal to +3. So we know that this is also +3. Now we have to check what are the electrons left. We know that it is this order.
Okay, basically the D group elements.
Yeah, so this is D1, D2, D3. This you will have to remember, and this is one of the most important factors that you'll have to take in consideration. Okay, and so this is D7 and this would be D8, D9, one second, D8, D9 and D10. So in this case, the options given are A is Mn, we have cobalt as D7, we have Fe D6
and chromium.
So that is D4.
D4.
So we know that this is the 3D orbital that we are talking about, and each of this has a 4 S2 which is full. So in this case, when it is +7, this will be left with 0 D0. CO will be left with single D6 because we'll have 2 electrons leaving from 4s and 1 from 3D.
Okay.
Fe will have D5, and we'll have Cr with d3. So we know that A option is the correct option because we have 0 d orbitals left in this, 0 electrons left in the d orbitals in this case.
So as you saw in this question, the firstly we found out the charge on the central metal atom by simple technique which we already discussed in the previous question as well. Then we looked at the electrons present in the 4s2 and the 3d orbitals of these metal atoms, and we found out that manganese with the charge of +7 and MnO4 minus had no electrons left in the d orbital, and hence it was the correct option. Let's move to the next question now. In question number 3, you are asked to state which of the following given coordination compounds are paramagnetic and which are diamagnetic. So this is a very important question, and these kind of questions are generally asked in your entrance examinations. So let's see the approach which we must follow while solving these kind of questions.
So this question is also, we follow it in the same way as we've been doing. We'll find the charge on each metal atom. In this case, you can directly see, based on your experience from last two questions, that the first one is Ni0 because carbonyl has a 0 charge. The second one is Ni2 plus because it is x minus 4 is equal to minus 2. The third one is again the same thing, Ni2 plus. So now once you have each charge on the central metal atom, you can then find what are the number of d electrons on each. So first we'll write down the charge like this orbital configuration for Ni.
Okay.
Ni as Ni0 has d9, 3d9 and 4s2. So that we can, it has 3d8. So we can draw the configuration,
The orbital diagram.
yeah. So that is 3, 4, 5, 6, 7 and 8, and we have 2 electrons in 4s2. So now once we have this, we can find for each basically for Ni2 plus also we'll find it the same way. In this case the 4s2 would be lost, so we'll have 3d8
Okay.
and 4s0. So this will be this way. This is under the condition that there is no field on the atom. Right now we just have the plain atom itself, like under no strong or weak field. Now we have to discuss one of the important concepts is that CO is a very strong field ligand, that it can cause strong pairing.
Okay.
CN is slightly weaker, but it is still strong.
Okay.
And Cl we know is a weak field ligand, so Cl does not cause any pairing at all. So next we will have to basically find out for each. So now we know that we had NiCO4. This had Ni0 and it has a strong field ligand,
Okay.
which is a very strong field ligand. So in that case that will lead to pairing. So we have basically this configuration, but it will go on to become this will be the configuration we will get, because the 4s2 electrons over here will be pushed into the 3d electrons, and the 3d2, the unpaired electrons which are there, will also get paired up. So this will be the net configuration we will have for this particular compound.
Okay, so this is only caused by ligands which are termed as strong field ligands.
Yes, carbonyl is the only ligand which is very strong, which can actually cause pairing from 4s into 3d as well.
Okay.
So this is something you must remember as well. So hence we know that there are no unpaired electrons in this case, and thus it is a diamagnetic compound.
Right.
So that is the first part of our question. So A part we are done. Now B, we have NiCN4 2 minus. So in this case we have Ni2 plus, and we have a strong field ligand.
Okay.
So this is the configuration we have to consider. But in this case we have a strong field ligand, so they will all again be pairing as we saw in the last case. So this will be the configuration we will get at the end of the pairing. So again we have n is equal to 0, the unpaired there's no unpaired electron. So that is why it is a diamagnetic compound. So in this case, the two unpaired electrons over here were paired up. So this electron was pushed into this orbital.
So both carbonyl and cyanide groups would cause this pairing in all coordination compounds.
Carbonide is the strongest, and carbonyl is the strongest field ligand, and cyanide is a very, very strong field ligand. This is something you will have to remember.
Okay.
And keep in mind the CFSE field strength of ligands, which is given in the textbook also, which is being taught everywhere, which you will remember. So next, the C part, we have to check for NiCl4 2-. In this case, we have Ni2+ with a weak field ligand. So in this case, there will be no pairing. So we will have to make the same compound that we made earlier.
Okay, the two unpaired electrons will remain as such.
Yes. So this will basically be the final configuration, and there will not be any pairing. So this is our final answer in this case. So we will have it this way. The 3d8 electrons, and this has two unpaired electrons, so it is paramagnetic. So this is our final answer, that A and B are diamagnetic and C is paramagnetic.
So the important concept which we learn from this question is the concept of strong field and weak field ligands. Strong field ligands will always cause pairing of unpaired electrons, as a result of which a substance becomes diamagnetic in nature. While in case of weak field ligands, if there is a presence of unpaired electrons, then they'll remain as such, and the compound will be paramagnetic in nature. So in question number 4, we are now asked to find the geometry of two coordination compounds. So let's see how we should approach the problems related to finding geometry and the hybridization of these compounds.
So in this question, we've been given two compounds. So first we need to find out the configuration for NiCO4. In this case, it is Ni0. So this is for NiCO4. So we know that this is Ni0. Now we know that CO is a strong field ligand. So as we've done in the last few questions, we'll find that it has all electrons paired up.
Okay.
It has a 3d10. So hence it has a 4s available and it has a 4p available. So the configuration will have a sp3 hybridization, which means that it will be tetrahedral, as you've already studied before.
Okay.
And the second has a pH3 ligand, which is a strong ligand. And in this case, we've been given Ni2+. So as we found before, Ni2+ has a configuration of... this is the Ni2+ configuration. But because this is a strong field ligand, the two electrons would be paired up.
Okay.
So we will have a... this will be the configuration.
So one of the d orbital would be empty now.
Yes. And hence we have a 3d8, 4s0, 4p0. And thus this will be the hybridization. So hybridization would become dsp2, which is a square planar configuration. So thus the answer will have to be a tetrahedral and square planar, B option.
So again the concept of strong field and weak field ligand comes into place, and it influences the way in which the electrons are donated by the ligand pair, and we get the hybridization, and from the hybridization we can find out the shape of these compounds. We have covered few questions related to the nomenclature and the magnetic properties of coordination compounds. Now we'll move on to the next important topic, which is isomerism. In question number 5, yes, we are asked to find out what kind of isomerism is exhibited by the octahedral compound shown. Now let's see how we'll find that out.
Okay, so in this question we'll have to check what all isomerism this particular compound can exhibit. We can directly see that it can exhibit ionization isomerism because it can possibly form these structures. It could have a Cl group outside the coordination sphere, and it could also have a Br group, a bromo group outside the coordination sphere.
Okay, why is that so?
Because the given compound has not been given in any particular configuration, where they've not given us in the question what all are inside the coordination sphere, and they've not given what all is outside the coordination sphere. So we can pair them up in any way we want. So in this particular question, we can pair Br outside, we can put Cl outside, we can even put NH3 outside. We can make it in any way. We know that it's octahedral, so there have to be 6 particular ligands inside the coordination entity. So that is how we will approach the question for ionization. So hence it is an ionization, it has ionization isomers. The second part, we can check whether it has geometrical isomers or not. So in this case, we know that it has geometrical isomers because if you take the first particular compounds, for instance, you can make 2 sets of isomers for this. You can make it in this way. So this is a trans wherein you have the 2 Br groups on the opposite sides. So this is your trans isomer. And you can make it also in this way, that you have Br and you have the 2 Br groups cis to each other. So this is a cis isomer. So we know that we have geometrical as well as ionization isomers. So the answer is option A.
So similar structures can be drawn for the other formula which you have shown as well.
Yes, we can draw more structures for other formulas as well. These are just 2 of those structures.
So as you have seen, this is the basic approach which must be followed in questions related to isomerism. You have to check whether it exhibits ionization or geometrical isomers by drawing its structure and then observing both the structures which you obtain. Let's now move to question 6. It will basically cover all the concepts which we have covered in the previous 5 questions. You are asked to match the columns in column 1 where a set of coordination compounds, the chemical formula of those compounds is given, and the set of properties are given in column 2, and we need to match them. So let's see how we'll approach this problem.
So for this problem, we'll have to pick each compound one by one. So let's start with the first particular compound. The first compound has 4 amine groups. It has H2O twice Cl2. So in this case, we directly know that it does have geometrical isomers because of the fact that we just did the last question where we saw that the 2 H2O groups can either be trans or they can be cis. So we know that it could be this way, that this would be trans and this would be the cis isomer. So we know that P is correct for this particular option. Now we have to find what is whether it is diamagnetic or it is a paramagnetic compound. So we can directly see that this is CO2 plus. CO2 plus, we know that it has, so we know that it is D7, right? So this is 5, 6, 7.
Right.
So we know that this is D7. So and we have so we can now find whether it is paramagnetic or diamagnetic. We know that it is paramagnetic because we also the S option is again valid for this because it is 2 plus oxidation
state.
And we have D7. So we have 2, 3, 4, 5, 6, 7, and it has to be paramagnetic because we have 1 unpaired electron in this case. For the next option, we have Pt NH3 2 Cl2. We know that platinum is 5D8 6S0 because it has Pt plus 2. It's got 2 Cl and 0 outside, so that is why S has to be correct. Again, for this case, it has to have geometrical isomers because it can have cis or trans again. This is a straightforward what we do in organic chemistry as well. Like a compound of CA2B2 type always has paramagnetic, always has
geometrical isomers,
cis and trans. Also, we know that in this case it is diamagnetic because we have even number of electrons, and NH3 being a strong ligand, they will all be paired up. So we can straight away tell that there will be no unpaired electrons.
So it's diamagnetic in nature.
So it has to be diamagnetic in nature.
So R is also correct for this case. So now for the C option, C has CO H2O5 Cl, as you can see over here. Now in this case we can check what the configuration for CO will be. This is CO plus 2 again, because
one Cl is outside the brackets.
Yes, we have one Cl outside the bracket as well in the question itself. The question had a
So
modification.
please make this correction in the question itself.
So now we have a Cl outside, so we have CO2 plus. Hence, it has to be S has to be correct again. In this case, this does not have geometrical isomers, obviously, because you do not have another entity. Like, it has only one Cl, so you cannot have two sets of cis and trans locations. So if you put Cl over here, all the others will be H2O, so it will always be the same. So you cannot have cis and trans isomers for this, so you do not have geometrical isomers. Now we can check whether it is paramagnetic or not. We know that cobalt is D7 and CO2 plus with D7 and with and it has a weak field ligand, so we know that it will have 3 and 4. So this is 7 electrons, so D7, and it has 3 unpaired electrons. So we know that it has D paramagnetism, so it has Q correct and S correct. Now we can move on to the fourth option. Fourth option has Ni, H2O6, Cl2. So this particular, as you can see over here, so this particular option we'll have to check the configuration. This is Ni2 plus again, so S is correct again for this case. Now we know that Ni is a D8 configuration for Ni in that order, so hence we know that this will have 3 D8 electrons.
Okay, and is H2O a weak field ligand?
H2O is a weak field ligand.
Okay.
So we will have paramagnetism because the unpaired pairing will not take place completely. So we have 5, 6, 7, 8. So we have 2 unpaired electrons in this case, and thus it will have paramagnetism because there will be 2 unpaired electrons. So for this option, Q and S are the correct options.
So again, as you have seen, we have now covered all the basic concepts which we discussed in the previous 5 questions. We had 4 structures, we analyzed them, we found out the oxidation state of the central metal atom, then we looked at the electrons present in the d orbital and the nature of the ligands, whether they were strong field or weak field ligands, as we have discussed in the previous problems as well, and those helped us in determining whether it had unpaired electrons or it did not have. Ultimately, and also we discussed a question on isomerism, and on the basis of the structure which we drew, we found out whether the compound exhibits cis and trans isomerism or not.